Hi guys, it's Fusheng here, and today I will be teaching you how to create a multi-class image classifier. And I use this multi-class image classifier for my final year project in Nanyang Polytechnic, which was deep learning with RC car. So this was the very first deep learning development in my project. So without further ado, let's get started. So first we'll take a look at the data structure of our file. So first of all, this is our dataset, and inside this dataset file will contain our data folder and our test folder. And we will use our data folder to train and validate on our training images and validation images. So I have 3000 images in total, so 1000 image for each class. And as you can see, I have renamed the files over here to look as car 0 to car 1000, and this will be the same for dogs, cats, and cars. So now that we have taken a look at the data folder, let's move on to the test folder. So the test folder will contain images of our test data. So do note that the test images must not be inside the data folder. So training and the data folder images and the test folder images are separate. So now that we've got that, we are going to test for our predictions. So before we do that, I have summarized this code into 6 simple steps where you can easily make a multi-class image classifier. So the first step is to load our data, but to do that, we first have to import necessary packages. So you might ask, what are packages? Packages are actually Python scripts which allow users to create features with it. So with a pandas package, I am able to create a data frame like this, and this is called a data frame. And a data frame is where we put all our data into a 2D array and display it like this. So let me explain the code. So first, in order to load our dataset, we need to specify a folder where we have our directory inside. So I created a variable called file names, and I specified my dataset folder over here. So this entire directory is needed. However, if you are using your current working directory, you can also avoid typing out the entire directory. So for example, my current working directory is under this entire FYP folder, so I can just delete this over here and it will still work. So once I've done that, I will be creating a empty list, and after creating that list, I will iterate through my entire directory. So I will use a for loop, and once I iterate through everything, I will create a variable called category, and this category is basically the class of the image. So I will split the file name of the image into an array. So I will take the first array of the file name and I will classify it as a category. So if the category is a car, then I will append an integer to it. So finally, when we output our data into the data frame, it will look something like this. So I will have cars as 0 and dogs as 2, as well as cats as 1. So once I've done that, I will want to double check whether I've categorized correctly all images. So to do that, I will just plot the bar graph, or I can plot the values, and I can use the F shape to show the total number of categories. So once I've done that, we can take a sample of our image and take a look at it. So once we have done that, we have come to the second step of our tutorial, which is to build a convolutional neural network. And to do this, we will first have to import the necessary items. So I'm going to use a sequential model in Keras. However, there is another model called functional API model, and I will touch on that in the next video, which I'm going to upload in a couple of days. So never mind that, let's continue. So next, I will import the layers which I'm going to use for this CNN network. So I'm going to use convolutional layers as well as max pooling layers and dropout layers. So right here, I have defined my model as model 2. However, you can just name it as model. It is fine. So I have model 2 equal to sequential, so I'm using a sequential model. And right now I'm going to use model.toAdd. So this specifies that I'm going to add a convolutional layer into my model. And once I've done that, you might ask, what is this number 32 here? And this number represents the features which are going to be extracted from the image that we put in to the model, that we feed into the network. So after this, we have a 3 by 3 bracket right here, and this 3 by 3 bracket represents the convolutional window which will iterate through the image size. And we are going to use a ReLU activation. And once we have done that, we are going to specify the input of our image. So width by height, we have 150 by 150 by 3. And this 3 represents the RGB value. And if you put 1, it will be a mono value, a mono color scale. So 3 is for an RGB color scale. So let's take a look at what this convolutional layer does. So over here, we have the convolutional layer, and this yellow box is the convolutional size, the convolutional window. And what it does is that it will pass through and iterate through the image, and it will extract the features from the image, and it will put it together as a convolved feature. So it will just join the features together. So once we have this is the convolved feature in the pink box here. So now let's move on to the max pooling layer. So once I add a max pooling layer, we have a pool size which I've defined 2 by 2. And this 2 by 2 max pooling layer represents the max pooling window size which will iterate through the convolved feature. And what this does is that it will downsize the image and retain all the feature inputs from the convolved feature. So let's take a look at it right here. So over here is a pooling layer. So we have an example of a 3 by 3 pooling window size here. And what it does is that this 3 by 3 window in the brown box will actually pass through the convolved feature box, and then it will gather all these features together in one place, which is in this blue box here. What max pooling does is that it takes all the features and it takes out the highest number of features from the network. So we can see that from this red box here, it takes the highest value of it. So this is the same for each box. So now that we have understand more about convolution and max pooling layers, let's move out to a dropout layer. So a dropout layer mainly reduces the complexity of a neural network. And what it does is that it reduces the number of nodes in the neural network and how much it is going to learn in the neural net. So once we have done that, we are going to repeat by adding another convolutional and max pooling layer. However, you see that there is a 64 instead of a 32. And this means that we are increasing the numbers of features which are extracted from the image. And what this does is that this will extract more features and make it even more clearer and complex. So once we have done that, we will get a flattened layer. And what this flattened layer does is that it will convert our images which we have fed into the neural network, which are 2D tensors, into 1D tensor. And once we have that, we are able to get the output of it. So you might ask, what is this dense layer for? Now this dense layer represents the nodes inside this fully connected layer. So this number is 96, and this dense layer is actually this feature input, which is actually calculated, is done by adding the first and second layer of convolution. So 32 plus 64 will give you 96. And once we have done that, we are going to add another dropout layer and a final dense layer. And this final dense layer here represents the number of outputs which we are going to predict. So since we have 3 classes, we are going to predict for cats, dogs, and cars. So once we have done that, we are going to compile our model. And to do that, we are going to use a categorical loss instead of a binary loss, since we are doing a multi-class image classification. Then after that, we are going to use an optimizer called Adam. Now, there are many optimizers you can use, such as SGD. However, I prefer to use Adam. And for the metrics, we are going to use accuracy. Now, once we have done that, we are going to summarize our model. And this model summary will show us the output shape of our model layers and the parameters inside. And this output shape is calculated with a formula, which I will link down below in the description so you can understand more about them. And the parameters represent the number of features which were extracted and how many features which the neural network has to learn. So it has to learn 8 million of them. One more thing that I would like to add on to this building of model is that for this entire fully connected layer, it contains your hidden input layers and the saved weights which we have in this neural network. And for this second dense layer here, which is 96, this feature input has to be the total number of convolution layers 1 and 2. You can use more, but make sure you add up the number of layers so that they are the same. Or you can also make the last convolution layer and the second last dense layer to have the same feature inputs. So once that happens, you are able to extract out the same amount of features. So I would like to highlight to you that when you have the total number of features in the convolution layers and it does not equal to the same number of dense feature inputs in your second last dense layer right here, you'll train and get a very bad graph, which will look like this. And this is mainly overfitting and underfitting. And if we look at the training results here for the first few epochs, you can see that it is actually fluctuating. So it goes up and down for all metrics. So to avoid this, you must make sure that your second dense layer feature input has the same amount as the total number of convolution layer feature inputs, or it is the same as the last convolution layer input. So once that is done, we are going to get callbacks, and callbacks are a function of Keras. So we have early stopping and learning rate reduction. So what this does is that early stopping will stop the training of our model when it finds that a metric is not improving. So when a model is not learning, then it will stop it. So we will stop training. So for learning rate reduction, it will reduce the learning rate to improve on the metric which we have specified. So we have specified the metric which is validation loss. And if validation loss is not improving, then it will reduce the learning rate so that it will improve in the next epoch. So we can of course set the patience. So the patience here represents the number of epoch. And for the learning rate, we will start from 0.01 and it will decrease. So we can set our callbacks to include early stopping and learning rate reduction. So once we have done that, we have come to the third part of our tutorial, which is to prepare our dataset. You can actually do this in the second step, then build your model. So building of model can come as the third step, but I prefer to do it in this way. So now that we have a data frame right here, which you have seen above, we are going to replace it with car, cats, and dogs. So you've seen that in our data frame it was 0, 1, and 2. So now we are going to replace it with a string. So now when we look at our data frame is in string for the categories. So once we have done that, I mentioned that we have a data folder, and we are going to split this data folder into two folders. So one will be the training and the other will be the validation. So if you don't want to create a data folder where it contains only images, you can also create two folders. So one folder is called a train folder and the other folder is called a validation folder. but I will save the hassle of time and I will do a train test split instead, which is faster. So I will call a train test split and I will split my data frame because all my data is inside my data frame. So I'm going to split it into 80-20. So my test size, which is my validation data frame, will be 20%. So and once we have done that, we can view the total number of images inside. So we have 2,400 images which we are going to train on, and these are the number of categories. And once we have done that, we have 600 of validation images. Now after we have done that, we can view the train and validation data frame, and I have displayed this file name here because some people say that it is not good for you to do a train test split. You should have a separate folder where you have a train folder and a validation folder. However, this is actually possible to use one folder and split it into two parts. So if we look at the data frame in the train folder, in the train and the validation data frame, our files are all different. So this means that we are not training or validating on the same image. And with this code here, I will prove that it is different. And once we have done that, we can say that it does not affect one another. So once I've done that, you can also choose to view it in an Excel spreadsheet. So you just save it into a CSV file, and you can alternatively view it there. So once I've done that, I'm going to view and double check the total number of train and validation images. Now once I've done that, I am going to data augmentate. And you might ask, what is data augmentation? Data augmentation is a way where we can artificially increase our data set. And what this does is that it will help our data to become larger. So for example, we have 3,000 images. It can increase our images to perhaps 5,000 or even larger. Normally, we will data augmentate on the train folder only. So what you have seen is this in this image data generator is that I have applied quite a few data augmentation features. So I have rotation range, so I will rotate the image left or right by the range value which I set as 15. Then I will rescale the image so that the neural network can learn the image, because if you do not rescale it, the computer will not be able to learn it. So once we have rescaled it, our image will actually be a set of zeros and ones. So once we have done that, we have also implemented shear range. So shear range will actually change the image of our feature. So if it's square, it will actually slant it, like sort of slant it like this. So we have also implemented zoom range, and zoom range will make the image zoom in, as well as horizontal flip. So horizontal flip will allow our images to flip over, and this is the same for width shift range and height shift range, where we will shift the image up, down, left or right by the value which we have set. Now once we have done that, our trained images, our trained model will be able to predict on images which happen to rotate or zoom in and are shared. So for our validation images, we are going to rescale them as well. So once we have done that, we are going to create the generators. So we will have a test generator and a validation generator. And I'm going to use flow from data frame since our images are from the data frame. So we're going to specify the train data frame, and then we're going to specify the directory here. And for the train generator, it is important to set the X and Y columns because this is the labels which it is going to learn on. So for the X column, we have the file names, and the Y column, we have our categories. And after that, we have to specify our target size, which is the image size, so 150 by 150, same as the input shape of our model. Then the class mode will be categorical, the same as the loss when you compile your model. And lastly, the batch size, and this batch size will represent the number of images you want to train in each batch. So if I specify a batch number of 32, I will be training on the first image to the 32nd image, and then the second batch will go from 33 to 64 and so on. So this will be the same for validation generator, and once we have done that, it will show an output which will show us the validated images for each class. So over here we have 2400 validated images belonging to 3 classes, and once we've done that, we are going to display our augmented images in the training data generator. So as you can see, some images have been rotated, some are zoomed in, actually all of them. So when we data augmentate our images, all our images which have been augmented will have the same feature. So they are zoomed in, they have shear range implemented, they have width shift range, height shift range, and etc. So once we have done that, we have come to the 4th step, and it is to train our model. So to train our model, first we have to specify the number of epochs which we are going to use. So as starting, I will be using 50 epochs, and for the batch size, it is needed to calculate the steps per epoch right here and the validation steps of our model. So I will give a regular batch size of 50. So a larger batch size will give you a shorter training time, while a smaller batch size will give you a longer training time. So you will want to have a batch size which will be a considerable and adequate amount in training your model. So not too fast and not too slow. And of course, it depends on your CPU power as well. So once we have done that, we are going to use model.fit generator, and we are going to train on the train generator. So we are going to specify the epochs, we are going to specify the validation data, validation steps per epoch, and lastly we're going to use callbacks. So once we have done that, we will be training our model. So as you can see, it's training the first epochs, and it took 100 seconds and 2 steps, 2 seconds per step. And as you can see, our metrics are over here. So our loss is at a pretty good value of 0.4, and as you can see, it is fluctuating around a minor fluctuation, but it is still around the same amount. So our accuracy is quite high. I would say it's around 70, close to 80%. So it is pretty good. And as for validation loss, it's around the same as loss. And also our validation accuracy is pretty good. So as you can see, as we train longer, we can see that the epoch here has a learn rate reduction. And from here in epoch 7 to epoch 8, you can see that it has decreased. Now, this is actually common when there are fluctuations in the training. And as you can see, it only stopped training at 12 epoch. So there was early stopping because the model did not improve. So let's take a look at the graph right now. So in this graph right here, we can see that there were many epochs to train. So our training looks rather okay. Normally it would be a beautiful steep curve like this. So however, in my case, it is just a straight line, so it did not really change. However, if you take a look in the graph here, there is a nice curve. You see, there's a nice curve for the training loss, and curves are normally seen in CNN networks where we train a good model. So normally there would not be any fluctuations in a good trained CNN model. So it will somewhat look like the training accuracy of this blue line. So let's go back. So looking at the accuracy, it's kind of fluctuating, but since our validation loss, which is key to our predictions, so a lower validation loss actually tells us that our model is doing better. It is learning the features better. So if you see that it does not improve at all, and it is keeping a steady number, probably 0.7, then most likely the dataset is very easy to learn. So it is actually learning the features very well, very easily. So it is not complex, which is good. And right now, once we have seen the graph, we have read the model, we have read the graph, and we have diagnosed it. So normally when we diagnose the graph, if the validation loss is higher than the training loss, that is overfitting. And that is when we will be using a dropout layer to reduce the overfitting, because overfitting will give us bad predictions. It will cause the model to predict on data badly. So with that, we can save and train the model. We can save the model after training. So now that we have saved the model, we can load our model. So this is to avoid retraining our model when we close and open our notebook. So we have come to the fifth step of our tutorial, which is to prepare and load our dataset, our test data. So this is similar to the first and third step. So instead of file names, I'm going to use test file names. I'm going to specify the test folder, and I'm going to put it into a data frame, and then I'm going to check, and I'm going to create the test generator. So for the test generator, we also have to specify the batch size. You can use 20 or 32, but I'm going to use 15. And once I've done that, I'm going to specify the X column. So the X column will be the file name. Since we do not have categories for the Y column, we are going to set it as none. Now we are at the sixth step of our tutorial, and this is the final step of our tutorial. So the last thing that we need to do is to predict on our test data. So we will have a test data file, and we are going to predict on it. So to do this, we are going to use model.predict generator, and we are going to predict on our test generator. And what generators do is that it will iterate through the image which is fed into the generator. So the generator will mainly iterate through every single image inside. So these images are all tensors. And once we have done that, we are going to specify the steps. So I'm going to use the total test image number divided by the batch size which I've defined for it. And then we are going to get our predictions. So these predictions are predicted in array. Because we have three classes, it is going to output an array with three values. So car, cat, and dogs are our classes in the test generator indices. And right here we can see that the highest number is dog, which is 6.59. So this will go under the class called dog. So the highest number in the array will be the predicted class. So to convert the value of arrays into integer, we are going to use np.argmax. So this will convert it, and we can see that our test data frame category will have integers. And as I've mentioned, that the trained class indices are the classes which we are going to map it. So now that we are going to map it, then we are going to get strings instead of integers. So these are strings, which is easier for us to see. So now that we have the string right here for all our predictions, we are going to view the total number of predicted classes in each class. So we have dogs, which is 68, car, which is 51, and cat, which is 31. So you can see a graph over here and the total number of images. So finally, we are going to look at the predicted label with the images. So we're just going to plot it using some code, and we can see that some are predicted correctly and some are predicted wrongly. So you can see that this is a dog here, and this is predicted as a dog. This is a cat, and this is predicted as a cat. However, for this as a cat, it is predicted as a dog. So I think that the predictions for this CNN network classifier is rather okay. So finally, what we do is to save all our predictions into a CSV file. So the ID here will be our file names, test file names, and the label here will be dog and cat. So these are the predicted labels. And do remember to check the description box down below to get the notebook from my GitHub account and download the dataset from Kaggle. I will include these links in the description. Finally, I would like to end off this tutorial. So if you guys found this tutorial helpful, please leave a like and subscribe. So I'd like to give some words of encouragement. So for people who are new to deep learning, I think that it is common that you will not understand lots of jargons in deep learning, and it is not easy. Personally, I have also been through that, and as we create a very simple deep learning image classifier using a data frame, I think that this is a good approach into stepping into the world of deep learning. And it is perfectly normal if your predictions are not 100% accurate, because you need to fine-tune your model. You need to test it, you need to do experiments, you need to play around with the models, you need to understand the nodes, the layers and stuff before you can create a very well CNN model which you are able to get close to even 90% or 100% accuracy of prediction to predict correctly. So with that, I would like to end off this video. Thank you for watching. Goodbye.